My name is YZ. In case you are curious, YZ is my real legal name. So first name single letter Y, last name single letter Z. I use YZ as my name on my publications for a number of years. I lost count how many. And at some point, I just said, no, why don't I change that? So a few years ago, I changed my legal names to YZ. So it's not just my initial. And so this is kind of reflect my philosophy of simplicity. So make my name shorter. Counterintuitively, I can make my name more unique. Another driving force is my kids. They are also excited to change their family name to be Z. So my kids also have their family name to be Z. And that was pretty cool when students call me Dr. Z or Professor Z. It makes me to feel like I have some, supervillain power. So all right, so that's me. And like Damon said, I got my bachelor degree in electrical engineering and computer science. You see a lot of affiliations. So my work is very interdisciplinary. By training, I got my bachelor degree in electrical engineering and computer science. And back then, I even spent some time on RoboCup. I don't know if it's still ongoing. So then somewhere close to the end of my undergrad study, I turned to the dark side and decided to study the most extreme and the most violent form of matter. So I joined nuclear. But nowadays, we're coming back to robotics because in order to make nuclear work, we actually need new robots. So then after graduations, 2 years at Oak Ridge, and then I started my independent career as an assistant professor, first at UIUC, Illinois Urbana-Champaign, in 2012. So, so I don't know if you recall this year, 2012, it was like a Maya prediction, apocalypse, and the end of the world. So interviewed at Illinois, they were like, the world is ending. Who cares? Let's hire this guy. So that's how I got started. And I stayed at Illinois, climbed the tenure promotion ladders, and stayed there for 10 years. So at the end of 2011 and beginning of 2022, so I had opportunities and gave a talk here. And you remember, like 2022, is when people began to see real people. My colleagues are very excited to see me in person. We're like, let's hire this guy. So that's how I got here. So I moved to Michigan in 2022. But seriously, so there are two main reasons that made my decision to move to Michigan. And one of them is, of course, my home department, nuclear, has been ranked #1 for many decades. Like where I graduated has always been #2. Then the second reason is many of you know, right? In 2022, the robotics department officially opened the door. I don't see myself as a 100% robotic person, but I really like the synergies between nuclear and robot. So I came here 2022, and in the last couple of years, have been like graduating my remaining students at UIUC, move some of them here, so trying to rebuild our capabilities and the research group. So so today I'm going to talk about some of the robots we built in our lab previously at the UC, and a little bit of some of the new robots we built here. So most of the robots I show here today are soft. So counterintuitively, the soft robots sometimes can even be more radiation resistant than traditional robots. At the end, I also talk about like 2 new robot systems we're building here in Michigan. It takes time to build hardware. We are still growing our effort. And I really hope to use this talk to stimulate some discussion and collaborations with students and faculty here in the robotics department. All right. I was fortunate to have a lot of good students, and shown here, I have 3 new students in my group here in Michigan. I think all of them are here: Lucas, Naomi, and David. Some of them work more on the physics side, some of them on the robotics side, and the other 3 are my former students. All of them have graduated, so they were the former students who did the majority of work I'm going to present today. Long, after graduation, he first joined Tesla, and after half a year, he couldn't stand Tesla anymore. It's too demanding. He moved to NVIDIA. But that was before the stock of NVIDIA took off. Like I think during the few years he was at NVIDIA, the stock of NVIDIA increased by 30 times. He can retire now. Then the other two students, Kevin Wonke, he did a lot of simulations of the self-robots, which I'll show today. He's now assistant professor at UIUC. And David now, he did underwater version, and you see all of them today. So David, after graduation, decided to launch his own startup. He's the CEO of the company named after him, like Now Robotics. Like Now is also his real name. His last name is Now. So yeah, so regardless, so I still have a lot of collaborations, my colleagues, my former colleagues in UIUC. I love them. We still write proposals, write papers together. Among the work I present today, one of the person that I really want to acknowledge is Professor Chris Hauser. He's in the CS department, UIUC, and we collaborated on the control of the soft robots. All right. For the robot work in our group, in the past, we have been sponsored by NSF and DOE Fusion Energy Sciences and the company Constellation, a nuclear company. Right. So let me get started. Like Damon said, I usually summarize the research in my group in two keywords: matter and machine. So M&M. On the matter side, we do statistical mechanics of complex systems, mostly material systems. I'm not going to talk about anything on that, but in fact, later on, see it has a lot of connections with the swarm robots work we do. So the other side of work is on robotics. So we've been working on, roughly speaking, 3 kind of robots. Previously, we spent a lot of effort on soft robots, and in the more recent few years, we get into swarm robots, like a very small robots, but not tiny, not micro, but it's like cookie size. And lastly, the wheel-like robot, kind of like the Unitree ones. But the overarching goal of robotic effort is want to bring robotics to nuclear applications, extreme environment applications. You might think this is it's trivial, right? So when you have a nuclear environment, radioactive, you don't really want people to get in and get the dose. It's not necessary. And you can like nuclear environments can be perfectly described as a 3D, right? So dangerous, dirty, dull. Sometimes it's dull, but sometimes it's pretty exciting. But I'll leave it there. So there are a lot of applications for robots in the nuclear field. Okay. So let me talk about like how we get into robotics first, and then I'll look back to nuclear applications. So in robotics itself it's not a new concept. We have known robots for more than several tens of years, maybe hundreds of years. So at the beginning, what we had hoped for are some like general purpose android that sometimes even more human than us, and maybe some crazy robot that try to kill us, and sometimes an obedient robot that can always help us to do different things, and lastly, maybe cute, harmless body. Okay, but we've been spending so much effort on robots, we don't have any of these. So the most useful everyday robot we have is probably this, right? So there's still a lot of work to be done before we can have the robots as we dream about. And that's why we still have a lot of people working on robots. And if you reflect a little bit about the pros and cons of traditional robots, roughly summarized here. So the traditional robots, they're very precise, very powerful, reliable, and they don't complain, right? So, ideal student. But on the other hand, traditional robots also have a lot of problems. They are usually made of metal. They're very heavy, and they consume a lot of energy, and they're very expensive. In addition to that, so when they fail catastrophically. Okay, so that's why oftentimes we don't see robots around us, and more powerful robots are kept in cages, so they're not human compatible. So one of the goals, I started work on robot, get back to working on robot about roughly 5-6 years ago, and that's after I got tenure. After getting tenure, I wanted to work on something different. So And the one goal we had is we want to free these robots from the cages. And at that time, like self robot was a really, really hot topic. There are a lot of development in self robots. The community is forming, and a lot of cool ideas. The self robots have become started to become mature field, mature community roughly about 10 years ago. And so we started to work on self robots. So in our lab, we try to explore different new soft materials. So in short, soft robots are made of a lot of soft materials. There's a few examples. We built some soft actuators, very typical actuators, and mention a little bit of our own contribution later on. This is for demonstration. We can lock in the actuator's location because of a patent we filed on a pinch lock. And then because of these soft materials, they are soft, but even without advanced control, they are safe around us. You can use it for like agriculture, fruit, vegetable harvesting. The last video shows it's a type of conducting polymer. When strikes the rubber, then the conduction change, and we can use that as a divided sensor. There are many ideas in the field. The benefit of soft robots are this here, so they're safe by design, and they're flexible, lightweight, and even wear them. They consume very little energy. And lastly, they are cheap. So they're like this, disposable technology. So in terms of applications, a lot of people in the self robotics field have been exploring applications in agriculture, healthcare, medicals, some proper human interaction, wearable devices. So we spent some time on that, and in the nuclear field, we're trying to think about like, can we bring self robots to nuclear applications? Are there any unique use? Right. So this is one of the early prototypes we built, starting from one actuator. We built multiple of them. And then we modularize the design of 3 sections, and they can be controlled separately. And you can see the 3 modules. You can already achieve the degree of freedoms impossible for traditional robots. So this looks very similar to a lot of the ongoing work in the field. And by the way, this is the real-time movie. I think our robots move pretty fast. So the particular innovation we did is it's not like we wanted beginning. So we wanted to find like tiny valves that can open and close the tube, the air tube, but we couldn't can anything as small as we can use in this. So we use a soft tube. A lot of other slides, but I'm not going to show today. So our idea is that it's kind of like our blood line. If you pinch a soft tube, then you can regulate the flow. So we use a micromagnet that drive a small pin that changes the pressure on soft tube, which allows us to regulate the airflow. And we can also completely close the valve. And response time is in the millisecond time scale. That allows us to do this really fast. And we filed the patent a few years ago, already approved. With that, because our airflows are regulated locally, compared to other self robots, like our self robots do not have that many tubes. Otherwise, for every valve, you need like 2 tubes, 1 input, 1 outlet. For us, even for the entire robot, we only have 1 tubes. So this way, the robot itself can be made more flexible. We can also extend that to even longer. Okay, so I'm gonna pause here slightly and change the topic to nuclear. Right? So what is the hard problem we must solve? So there are many hard problems nowadays we're facing, and this is the hard problem, not that we want to solve, but we must solve. So what I mean by that is energy. And this is a chart that shows the global energy consumption as function for time, and also separated in different categories. So for a very long time, like before 1900, humans really did not consume energy. And this really takes off from roughly 1900 or 1950. Actually, after 1950, because of the advancement of modern technology, the human consumption of energy really has taken off, and even more so in the last few years. If you look at the different type of energy source. So we're still burning some traditional biomass. A lot of them come from the fossil fuels, coal, oil, natural gas. And there are more and more development in the new energies. Nuclear is one of them. So in short, there's going to be more and more demand in terms of energy. The question, how do we solve that? Well, we can keep increasing the mining of the coal and oil, natural gas. Probably, I think they're probably going to continue. So of course, they are not perfect because not only because of the polluted environment, even worse, they are very valuable resources. So if we burn them, we cannot regenerate them anymore for a very long time. So we don't want 100 years later when our future generation find new use of oil, they say, our idiot and sensor have burned all of them. Right? So even though we can, but it's better if we can find some alternative energy sources. Nuclear is one of them. On the other hand, in terms of energy demand, so there are, so in addition to the traditional sectors, two new sectors have even more demand in terms of energy. So this slide shows the energy demanded by the electrical vehicles. And there are three plots, the one in the middle. So this shows the annual energy demand for electric vehicle from 2018 to 2023. So it's growing like more than linear. And if you look at by month, so in 2024, this paper, they don't have the data, but they compare the demand for the first 2 months, 2022, 2023. So this is still growing faster and faster. And if you look at the comparison, next one, if you look at the comparison of the EV demands of energy, now it's a big piece of the big pie. So the second driving force of energy is data center. This is because of AI, there's more and more need of data centers. And this is one slide that shows the global electricity growth of several different categories. So now the growth of the data centers even more than like our space and water heating is comparable to cooling and appliances. And this is why, like all of a sudden, in the last couple of years, a lot of high-tech companies started to look for energy sources to power the data center. And in a recent McKinsey report, it shows like the energy center demand since 2014, and the project, and we are right here, like 2025-ish. So in the last 10 years, also we have been adding like roughly 10% per year energy demand from data center. This trend is only going to keep growing for at least for the next 10 years also. So, and where does those energy come from? Right? So still need to produce electricity to power what data center need. That's why all of a sudden, a lot of billionaires and also venture capitalists and high-tech companies start to put in like a ton of money in terms of nuclear energy. So this was some of the highlights. You can see like Bloomberg as a highlight, high billionaires writing around nuclear and energy crisis looms. By the way, all of them are in the last 2 years, like 2022, 2024. In the New York Times, also nuclear power is hard. Climate billionaire wants to make it easier. CNPC, Vice Silicon Valley for hot nuclear energy. So the nuclear news flash. This is an interesting figure that shows the number of investment in nuclear startups. So there were almost nothing like before 2020, but since 2021, the entire field exploded. Like this private investment put in almost $4 billion of nuclear energy. And it's trying to keep growing. In the last 2 years, also see almost all these big tech firms like Amazon invest like 500 million, invest in X Energy. Google invested its Kairos Power. Microsoft, the TerraPower is kind of the counterpart of Microsoft. It's also funded by Bill Gates, but actually has been there for a long time. Microsoft has also signed the exclusive use with Constellation to restart the 3 Mile Island nuclear power plant. OpenAI, all of them will be spending a ton of money terms of nuclear energy. But in addition to this effort, there are also like more than 100 smaller startup companies that are trying to explore different ways to produce nuclear energy. Some of them use fission, some of them fusion, and this is still ongoing. On the other side, there's also a lot of investment from the federal government. So this chart shows the recommended R&D funding for nuclear in the last 10 years also. Yes, roughly 10 years, from 2021 to 2030. It's different categories of nuclear energy, environmental R&D, enabling science technology, radiation facilities, and lastly, the demonstration. Demonstration is the last stop that before we can commercialize those nuclear power plants. And see, it's like many billions are invested in this field. I know like nowadays a lot of uncertainties in funding situations, but most people, including myself, is very hopeful in terms of nuclear. And why is that? You can see, not too long ago, May this year, a couple months ago, in one day, on May the 29th, the Trump administration issued 4 executive orders to promote nuclear energy, employing advanced nuclear reactor technology, national security, changing the reforming the NRC, and reforming the nuclear testing, and another way to reinvigorate nuclear industrial base. So we anticipate that the investment from both the federal government and also the private sector keep increasing in the next few years. So this is the big problem we're trying to solve. Now, coming back, what role can robotics play in this nuclear renaissance? So in the past, we have been building soft robots, and I'm going to show you some of the use cases of soft robots in nuclear environments. So when we started to work on soft robots, they're not like traditional robots. You really have to make a 3D module and build a robot and then collect the data and test them. There's not a lot of almost none simulation and control environment. So we started working on that. So the first work we did is related to modeling and simulation soft robots. So you can indeed use some analytical models, use ROD, you can use curvature models. So they are very efficient for compute, but they have very limited expressivity. Usually, you assume the robot is one-dimensional. So overall, you can do that. It's very helpful to understand the motion robot, but they lack the details to compare with the real robots. A more realistic method is to use a finite element. Finite element is accurate, and you can also incorporate not only the deformation materials, but also all the other physics. Bring heat transfer, bring the fluid mechanics. So there are multi-physics, but the problems of finite element is they are very expensive. In that you have to spend a lot of CPU power to do the calculation. So the one research direction of my former student, Kevin, was to develop simulation environment software for soft robot. So we created a simulation environment we called Kraken. So Kraken is built upon a MOOS framework. So for those who are in nuclear field, may have heard of MOOS. MOOS is a large-scale finite element framework, and provided by many different components of the packages supported by DOE, Department of Energy. Originally, MOOS was created to simulate a nuclear reactor, fuel performance, etc. So on top of the MOOS framework, you can build apps. They also call it apps. It's open source. It by design supports multi-physics and so provide high accuracy modeling. So, but it's not designed to simulate soft robots. So we took the MOOS framework and built an app on top of the MOOS, and which we call Kraken. So in particular, we added 3 features. So MOOS, the nuclear field, does not usually have hyperelastic materials. So first, we added a capability to simulate hyperelastic materials. And then I had the capability to simulate the dynamics or kinetics of the soft material. And lastly, we have to deal with the soft contact. without self-contact, the self-actuator wouldn't bend. So these are the three features we implemented. So I'll go through them quickly. So the first one is hyperelastic modeling. Usually, there are a couple of other simulations of the simulation of robotics of frameworks in the field. Most of them treat the material to be linear, so they don't really directly have a hyperelastic materials. That is only correct when you don't have a large deformation. If in a linear regime, then the linear approximation is good. But when you go to very large deformation, we have used the hyperelastic model. So this shows the straight strain curve of these soft materials, and the linear elasticity is here, but the actual elasticity, the actual deformation follows either the green or the orange. It's different materials. So we implemented this hyperelastic material simulations in the framework. And so how we do that, more details into that. So in order to calculate the straight strain curve, we first deform the material, and we calculate the deformations material. From there on, we can compute the two quantities. One is the so-called left Cauchy green deformation tensor. The second is the local volume. Based on these two, and also some material properties, we can calculate the true stress of the material. Okay, so this is some demonstration of our simulation. We start by stretching a rod, a hyperelastic rod. The only stretch a little bit is elastic. If you keep stretching that, then the hyperelasticity start to show up. Let me see. So in this figure, can show one of these two lines on this curve. One of them is our simulated new hooking, is a new hooking model. The other theoretical stress, and they agree with each other. So for linear elasticity, you can only go to like a 1%. Sorry. Okay. And then we build actuator, the very simple actuator everyone uses. We build the actuator. We can also stress the actuator and has a stress strain curve. And this has a somewhat good result compared to the instrumental method. So build actuator, infer the material property. By the end of the day, you can see the smoother curve is our calculation, and this rougher one is the experiment. So we can model this hyperelasticity in the soft robot. So the second problem we faced was because the soft robot itself is soft. So oftentimes when move the robot, they are not very stable. They oftentimes either unctuated, they oscillate. So only being able to simulate or understand quasi-static configuration is not enough. We need to be able to simulate the dynamics of the soft robot. So within our environment, the Kraken, we added the capability to model the dynamics. So this is a demonstration to show that we can simulate the deformations, two-dimensional robot arm. Later on, we have a real one, but this is help us to both control the robot and also iterate the design process. Okay, so this is another demonstration to compute the dynamics. The time scale is not linear. That's why you see it's not very smooth. We accelerate the simulation so that we don't need to sample the unnecessary time steps. So this is in this comparison, we show that we can model the really damping of a hyperelastic actuator. And sometimes we really want to try to go extreme to see if we can simulate some more complicated motions. So we took like one actuator, again, it's a very simple one. The deformation hyperelastic, and we put the weight at the bottom. Then even with this, the system itself is nonlinear. So we have this hyperelastic pendulum can swing, and you can at the same time the pendulum will swing, and the actuator can also expand and contract. So there's a lot more computation how to do, and this is the complex systems. We really cannot have exact predictions, but now we cannot do that for a long time. A short time, that's pretty good. So the left-hand side shows the actual measurement of the locations of this actuator. The right-hand side shows the simulation. The actual trajectory itself actually is irrelevant. What is important to look at our spectrum, the prediction of our simulation experiments pretty well. So this opens a way to not only simulate the static configuration of solved robot, but also the dynamic. It's very important for solved robots. So the third feature we had to implement in order to simulate solved robots is the contact. So solved robot can move because of contact. So original Moose framework does not have a solved contact. Usually computing the contact mechanics is very expensive. So we had a smarter way to we add a helper body, kind of separate the two different components that help us to speed up the calculations of solved contact mechanics. These are some demonstration to show that now we can inflate the actuator and then simulate the deformations of the solved actuator. And right-hand side shows that not only we can simulate the soft contact, but also solve the hard material contact. It shows that with like 3-finger gripper that grips like an object with some arbitrary shape and would leave that off the ground. So now we're able to simulate all of them on the computer. So that can help us with both the design and also control of the robot. So undoubtedly, so like when we publish the work, we're contacted by like the company. So this is why I'll explain, like, why do I have a simulation like this? What is the shape? So this company makes prosthetics. They make artificial hips. And so they reach out to us because one of the major costs of their product is to actually make the package. So you have to package the hip in the form. So they wanted to know if we deform the hip, if you can try to make it flat, then can make prediction like what its shape looks like. It's pretty simple calculation for us. We did it for them. This is the artificial hip. So so in short, so this part of work was really done by one of my students, Kevin Keith. So I did the 3 components into this framework. We have a simulation package called Kraken. This allows us to simulate the hyperelastic material deformation, the dynamics, and also some efficient solved contact. So with this, now we can really help speed up our manufacture of the solved robot. And so now I'm trying to connect this token. So you see like the one in-air version of solved robot arm, and it moves pretty fast, but they wobble. And one of the problem or challenge for solved robots is the solved robot has to handle the weight of itself. So the only pure solved animals in the world are in underwater, like octopus. So so we decided to move to redesign our solved robot arm and put it underwater. This is also because of nuclear reactors, we have a reactor pool, and we need a robot arm that can resist the radiation, can also operate underwater. So we did it. So this shows that the
just do some crazy movements like you were doing. We haven't seen that yet on the video.
So the size of the arm is basically the size of my arm. Not extended. I'll add a brief idea similar to our previous design. When this case, we only in air, the environment. If you watch carefully, you might be able to see air flows, sorry, water flows. And with the multi-physics simulation package, we can simulate the deformation even underwater. We can simulate fluid mechanics within the actuator as well as formation of the hyperelastic material. And I have an accelerated version. Acceleration, you can see the flexibility we can achieve in underwater environment. So again, we found another patent. And so the other benefit of a solved robot like that is, especially underwater, we can tune the density of the robot to be very close to density of water. So they are neutrally buoyant. So we don't have to worry about the weight of the robot itself. And flexible, you can use the robot arm to go around obstacles to grab things. So that we'll put a pillar in front of the robot, but because of the flexibility of the robot, then we can use the robot to grab something behind the obstacles. So in fact, this is oftentimes very much needed in a nuclear reactor pool. So although you might think that you really do not want to drop anything in the reactor pool, but in reality, a lot of them get dropped in the nuclear reactor pool. And it's very, very expensive to remove them. For our soft robots, because we pump water from the environment, but nothing is 100% radiation resistant. Everything will fail eventually. But for our robots, they are somewhat more radiation resistant than traditional robots because we make it soft material. Soft material become harder and harder under radiation. Eventually, they are going to fail. But when they fail, to replace them. This can be modular. Every section is cheap and replace them. So this is the benefit of having soft robots instead of traditional robots. There are a lot more applications in this environment. So if this seems familiar, you might have seen that in Spider-Man, right? So to look at even the design of robot arm, it's very similar to Dr. Octopus. I watched the movie a long time ago, and I feel like no real person can carry those metal arms. So what we are trying to do in our group is we try to build like soft Dr. Octopus. So interestingly, do you still remember like why Dr. Octopus created those one arm in the first place? Nuclear, right? So because Dr. Oct needs to achieve nuclear fusion, then he needs these arms to put in I don't know if you mentioned the movie, like deuterium and tritium together to ignite the fusion process. So yeah, so Dr. Oct is indeed a nuclear scientist, created the robot. So and there's a lot more behind the scene, which I'm not going to be able to show off. But this is
in this video, we show trajectories of the robot as it tries to reach a few different targets using different controllers, as shown in our paper.
Robot itself is very challenging.
The open-loop inverse kinematics, visual servo, CQL, and TRPO controllers are benchmarks, and the auto MPC controller is shown in comparison to them. The panel on the bottom left shows some real-time details of the experiment, such as time outside the goal region and current distance between the end effector and the target. The panel on the bottom right shows pressure readings in each of the corresponding hydraulic actuators. In each of the selected experiments, the auto MPC controller is shown to outperform the benchmarks in terms of final distance to target and time outside the goal region.
Yeah, so this work we collaborate with my former colleagues, Chris, and so they have developed this automatic MPC matter multiple control that can automatically tune the hyperparameters. And we show that with auto MPC, at least for the simple robot, we can achieve better performance than traditional robot, the traditional controller. This is I don't think I'm gonna finish all the movie, but want to know details, you can take a look at the paper. The paper was published in RAL a couple years ago, 2023, presented at IPROC. So anyway, so moving forward, there's still a lot of work to be done in the field of soft robots, and I'll be reflecting like what are the technical challenges. So David and I have been writing this paper, and it's being reviewed now. We gather a perspective article and to try to put all the challenges that prevent us to build a practical soft robots into 4 different categories: the material challenges, energy or battery challenges, sensors, computing, including control. So hope this paper will be released soon. Anyway, so a lot of our previous efforts have been devoted to soft robots, and we're still interested in that. After moving to Michigan, I tried to expand to 2 new directions. So one of them is swarm robots, the other wheel-like robots. I'll mention a little bit for the remaining time. So swarm robot. So swarm robot is a collection of many robot systems, and they're also motivated by movies. So here I show you the cookie bot in this Speak For Me. In fact, this is exactly the one we are making in our lab right now. Probably have watched too many movies. And then the other one is the even smaller one, Microbot in Big Hero 6. Our robot is more like this cookie bot. So the idea is that even with one simple robot, has a very limited function, but you have a large amount of them. Collectively, they can show some higher level intelligence. They can accomplish tasks that is impossible for traditional robots. And these robots are also cheap. Otherwise, we cannot make hundreds of thousands of them. And just like a ant, one or two ants die, it doesn't affect the entire swarm. So we wanted to make a robot there. And there has been a lot of work done in this field. And we try to build upon what other people get more controls of individual cookie box. And thankfully, I was really fortunate to be able to attract a lot of talented students to join our team and call our robotic team to be item-bound. This is the list, I think, of current students. I think we have more than that, but this is all the pictures we can find yesterday. So in the last year and a half, 2 years also, roughly I counted roughly about somewhere between 60 and 80 students have contributed to our project. I cannot list all of them. So these are the group of our current students who are making contribution to our item-bot project. And this is a small movie of one of the early versions we made. So it's vibrator-based, kind of like HackSpot. They're based on vibrators. Added more control so that you can control how they move. So they're still very cheap. We don't use wheels or many wheels because of we still want to maintain the low cost of robot. And they're very low profile. And so in the future, we can my clients put some like sensors on top of that, so they can go underneath the table. They can just like the cookie bot, and they can be used for information collection, surveillance, etc. Another movie shows this is I think the version we had last year. We're able to improve the design and invite multiple of them. They can communicate with the central server. But we're still making more and more iterations to improve this. So this is the like one research direction we are exploring right now. Again, I'm really fortunate to have a student who have strong interest, so they're working very hard on this. I hope in a couple of years this research field will really grow. So the second robot, I don't really have a cool movie to show. Is we also wanted to build a wheel-like robot. So it's kind of like a Boston Dynamics spot, but with wheels on it. Again, they're motivated by a lot of movies. So we're working very hard to build this wheel-like system in a way they are similar to the Unitree robot. So when we started working on that last year, like Unitree has not really announced that yet. So anyway, so that's the second system we are building. Okay. I'll try to wrap up this before 4 o'clock. So so in short, lastly, there are a lot of applications of different robots in the nuclear field. So here I want to show you like two information that I think might be relevant to many of you. On the left-hand side, we organized one workshop at the ICRA, the robotic conference, back in May. I'm one of the organizers. So, and this has been running for a couple of years. I think it's going to continue. So there's growing interest in the application of robots in the nuclear field. Current challenges in robotics for nuclear development. If you happen to be in ICRA, or if you have some work related to this, please contribute to this workshop. So the second effort is a part of ANICE. Oh, by the way, this is a co-organized by ANICE, American Nuclear Society, and IEEE. The right-hand side shows the robotic division under ANICE, American Nuclear Society. I'm the secretary of the division, and this division has grown a lot in the last couple of years, and we would like to more people be aware of this division. For students, we join our division, and for the first year, we'll cover your membership fee, right? The free for you. So, and every 2 years also, we have invited a meeting at the nuclear conference where you can see a lot of development of like applied robotics for nuclear applications. Okay. So lastly, allow me to brag about this. So from time to time, we also do like outreach activities. We take like elementary school students into our labs, and sometimes they're very nice. They send me cards, and you can see this is still before I change my name. So they are very cute. And if I can highlight the one particular one, this is the one note written incomplete. It is an incomplete fifth grade girl. She mentions thank you, etc., etc. Towards the end, you can see it. My favorite part. Okay, I've been interested in robotics for a while, and you have inspired me even more to be an engineer someday. So when I saw that, my heart really melted. So from time to time, I have a dark days as well, and every time when I see side will hide on me. So this is the light behind. All right, so I'm gonna stop here and end up with a quote from Lawson. So that the soft defeats the hard and the yielding conquers the strong. So there are a lot of applications of soft robots in the very, very hard environment. Right, I'll stop here. Happy to answer any questions you have.